The next example of an ordered structure we consider is Fe3Al. Now, as we are going from the simple ordered structure to more complex ordered structures, we will have to use certain techniques to understand them, certain techniques to visualize them, and also we will come across certain concepts which we have not considered before. So, these examples are not just examples of ordered structures, but they additionally serve to highlight certain aspects with regarding especially to for instance the coordination of atoms, etc., which we have not dealt with before. In Fe3Al, as you can see, it is a large unit cell, not very large, but larger than some of the simple atoms we have considered, simple elements we have considered so far. It has got a lattice parameter of about 5.8 angstroms. It has got the complete cubic symmetry, which is F 4 by m 3 bar 2 by m, and there is this notation which is known as the Structure-Bereisch notation, in which it is given a name of DO3. So, it is one of the rather popular structures. In the Pearson symbol, it is cubic, face centered, and there are 16 atoms in the unit cell. So, how do I count the 16 atoms in this unit cell? So, again, even though there are so many atoms, the lattice is still our face centered cubic lattice. That means whatever atom apart from the face centering position, so you can see there are atoms in the face centering position, the blue atoms, whatever other atoms are have to go part of the motif. So, we have to calculate the 16 atoms in the unit cell, and how do we do that? So, we can see first let us start with the calculation of the iron atoms. So, the iron atoms are the ones which are occupying the corners and also the face centers, and in addition I have also shown them by these light blue colors. So, the dark blue and the light blue colored atoms are iron, and we shall see they are actually in some sense different kind of ions. So, we will see that aspect in a coming slide. So, let us first make a calculation of number of atoms per unit cell. So, you can see that totally all the 8 atoms in the vertices 1, 2, 3, 4, all the 8 atoms together give us a contribution of 1 iron atom to this unit cell. So, vertex atoms 1, there are 6 faces and there is iron atoms at these faces, and together they give a contribution of 3 iron atoms to this unit cell. Then we have this other iron atom which is located at quarter position. So, this is the quarter position, and if there is one here, according to the face centering this symmetry of this point group and the space group, we will see that there has to be an iron atom here, the 4-fold will take it here, there will be one more here, there will be one more here. So, this will be a position like quarter, the second position will be a quarter, 3/4, quarter. So, therefore, you will have other positions, and there you will have 8 atoms within the unit cell. Therefore, all the 8 which are contained within the unit cell will go as contributions to this unit cell. They will have 8 iron atoms located in this quarter position and other equivalent positions. So, therefore, what is the total number of iron atoms in this unit cell? 8 from these, which I call the iron 2 atoms, and why I call them the iron 2 atoms I will explain in a moment. Then 3 from the face centering positions and 1 from the vertex, making it a total of 12. So, I have 12 iron atoms in the unit cell. So, and let me count the number of aluminum atoms. The aluminum atoms are the ones which are in brown, and you can see they are all located at the 12 edges. So, from 12 edges with 1/4 contribution to this unit cell from each edge, therefore, I have 3 iron atoms which come from the edges. There is one more iron atom located at the body center, aluminum atom located at the body center, therefore, that gives a contribution of 1, therefore, total of 4 aluminum atoms in this unit cell. So, I can write the chemical formula of this unit cell as Fe12Al4, and I reduce it to the common factors and make it Fe3Al. So, this is my reduced chemical formula, but if I want to use a complete chemical formula for the unit cell, I will have to write it as Fe12Al4. Now, as I told you, I will use these slightly more complicated examples. So, this is obviously these are more complicated atoms, there are more number of atoms in the unit cell, there are 16 atoms in the unit cell, unlike some of the simple structures we have seen before, wherein they are just 1 or 2 or 4 atoms in the unit cell. Therefore, I need more and more techniques and more visualization so as to understand these structures in as simple a way as possible. Of course, later on in this course, we will see more complicated examples wherein no simple visualization is possible to understand these structures, and they will continue to remain rather complicated structures. But wherever possible, we will try to understand them in some of the simple terms we have used so far. Ravi has a question.
Sir, what are the factors that will determine that these atoms will sit on the FCC position?
Okay. his question is that what will determine if these atoms sit in FCC positions or some other different positions. Okay. Now this is actually a very profound question, and some aspects of this question we will address later. Okay. That even the very simple question, why does for instance iron form an FCC face centered cubic crystal structure, or why does for instance chromium form a BCC crystal structure. So these are somewhat profound questions. There have been techniques and approximations to understand these crystal structures in terms of the energetics, but nevertheless to understand larger and larger unit cells like this, the overall the computation and the techniques get more sophisticated, and it becomes a rather profound question. To answer in one line, actually we will have to solve the Schrodinger equation for the entire crystal, which is, as you can see, a very complicated task.
So is the position of iron and aluminum interchangeable in these crystals? As in sodium chloride, we can put the sodium and chloride on the.
Clearly not, because you can see the stoichiometry is so different. If I did the interchanging, then my stoichiometry will completely change, at least for this example. But there could be other examples wherein, for instance, let me use the same space as board, so do not relate it to this crystal structure, but this space is meant for general explanation. So I can see that you could have a structure wherein an A3B is stabilized, and it could also be possible that the same phase diagram also shows an AB3. Of course, A3B and AB3 need not have the same crystal structure, but there could be special cases wherein A3B and AB3 exist, wherein the crystal structure is obtained just by merely interchanging the position. So there is this possibility existing, but not in this particular example Fe3 here. Within the example, if I change it, then I am obviously changing the stoichiometry. Now I mentioned that I am designating two different ion positions. That means I am calling one as ion 1 here, another ion as ion 2, right. Now I need to understand this, and to understand this, though we have not gone into the detail of this what you known as the Wyckoff position, etc., these have been designated, for instance, in Wyckoff notation as 4a and 4c. So we will not take up details of this, but we will understand it in our normal knowledge of coordination polyhedra later. So the ion 1 is located in 0 0 0 an equivalent position, the ion 2 is located in quarter 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 positions like these and equivalent positions. So we try to understand, and we will also notice that there are other examples of crystal structures which go into this DO3 kind of crystal structures. So the DO3 has basically no science behind it, it is just a listing, while CF16 we have already seen the rationale behind using this kind of a Pearson symbol. Okay. So let us try to understand this structure a little more. So this is a space filling model of the same, wherein you can clearly see the aluminum and iron atoms touching each other, and this is a 1001 view of the same. So the only way to understand such complex crystal structures is to actually try to visualize them from many angles, try to understand the various kind of models we have dealt with before, like we told you, the space filling model, the ball and stick model, the wireframe model, etc. So you can see clearly from this that the normal phase centering positions are occupied, for instance this and this, but additionally these are these other atoms which are located at quarter quarter quarter. So this is my quarter 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 kind of atoms, the ones here which you are seeing from the side view, which in the previous view you can clearly see are these atoms. So you can see those atoms from this side view, and additionally you can see the space filling view of this entire ordered crystal structure. So I was mentioning that I am using two designations for the iron atoms, while I am using only one designation or one position for the aluminum atom. The aluminum atom is located in the corner position and all the phase centering positions. So this, it is very clear. So and this atom is related to this other atom of aluminum by the standard phase centering translation. So there is no problem. There is no other for instance no other atom located anywhere else which I need to consider. Now let me look at the coordination polyhedron around an iron atom which is located in the corner and also at the phase center. So this is my iron atoms. So let me go back to this original site. So what I am considering here is my coordination around the aluminum atoms, coordination on the iron atoms which are located here, and the coordination around the iron atoms which are located in a different position. Now if I look at the coordination around the what I call the iron 1 position, which is 0 0 0 position, and as I told you, because this is a face centered cubic kind of structure, the lattice is face centered, so any other atom which is located here also has to be identical in terms of its environment, because that is a lattice position. So that is clearly verified. So if you look at an iron atom here, you can clearly see you have a cube of iron around it. So the coordination polyhedron around this is 8 iron atoms or ions around this central iron ion. Similarly, the cube would be identical when I look around the ion which is located at half 0, which is related to the phase centering translation to the atom at 0, 0, 0. Clear? So, there is no problem with respect to this. Therefore, but now I would like to contrast this kind of a coordination with the coordination of an iron atom or an ion which is located at quarter, quarter, quarter. So, this is I am contrasting the coordination shell around the atom which is located at 0, 0, 0 with the coordination shell around an atom which is at quarter, quarter, quarter. So, let me look at the coordination shell. So, first let me try to identify atoms of the same type which sit around this. So, let me see that if I try to observe that, I will see that there is a tetrahedron of aluminum around this central iron atom. So, this tetrahedron is formed, as you can see, with 4 iron atoms which are located at the edge centers and the body center. So, this is my tetrahedron of aluminum around my iron which is located at quarter, quarter, quarter. Now, I could alternately visualize a tetrahedron of iron located around the same iron atom which is at the center, which is the iron 2 atom, which is my atom which is right here at the middle here, and you can see that this is a tetrahedron of iron. But the coordination polyhedron is not just this tetrahedron of aluminum or this tetrahedron of iron, but is actually a combination of both of them. In other words, it is a cube, but now all the vertices of the cube are not identically populated. As you can see, this whatever the subset which is this tetrahedron is populated by aluminum atoms, and this tetrahedron is populated by iron atoms. So, I can draw this subtetrahedron within this by joining these atoms, for instance. So, I can complete this tetrahedron, like I will find there are 2 tetrahedra like this, and therefore, what I have around the central iron atom is a cube half populated by aluminum atoms and half populated by iron atoms. So, clearly my coordination environment around the central iron atom which is located at 0, 0, 0 is different from the iron atom which is located at quarter, 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 which is clearly designated by looking at the Wyckoff positions here, which is, and in other words, there are iron 1 is a 4, contributes 4 atoms to the unit cell, therefore, there is this 4a position, and iron 2 there are 8 atoms, therefore 8c. So, clearly they are non-equivalent positions is with regard to the coordination polyhedron, and number of such equivalent points or equivalent atoms within the unit cell are also different. So, there are 8 belonging to this type and there are 4 belonging to this type, and this calculation is easy to make because we know there is 1 contribution from the corner atoms and 3 from the phase centering atoms. So, there are 4 of this type and there are 8 of this type. So, that much is very clear. So, this example is a beautiful example wherein we have now not only understood more complicated versions of ordering. So, let me revise some of the ordering we already see in the simpler versions of ordering, like, so we started out the very simple form of ordering wherein a BCC crystal in the copper zinc system became a simple cubic crystal, and we could describe this in terms of 2 sublattices. Now, we considered a little more complicated example wherein now I have a ordering. So, in other words, the phase centered the disordered structure would be a phase centered cubic structure, and the ordered structure would again be a simple cubic structure, which is now again indicated by the P, which means it is a primitive structure. So, I have a primitive structure which is my ordered structure. Again, that means that whatever other atoms are located apart from the corners, which are lattice points, have to be accounted for in the form of a motif. So, that part is absolutely clear. So, it cannot be part of the lattice. So, these are all not lattice points, only lattice points or the corners. So, even this was reasonably simple as compared to the last example we considered, and we could understand this in terms of a derivative of the FCC lattice. The Cu3A, which was the next example we considered, and here again it was considered as a derivative of the phase centered cubic lattice, and again we saw that the stoichiometry is not a 50-50 stoichiometry. It is for every atom of gold we had 3 atoms of copper or 3 ions of copper if you want, and this again can be thought of as a derivative of the phase centered cubic lattice, but the structure itself, the ordered structure, is a primitive structure and not a phase centered cubic structure. Again, as before, since the primitive structure, the only lattice points are at the vertices of this cube and not any other point, therefore, every other atom in this has to go part of the motifs. So, the motif now will consider, for instance, one possible choice of motif is this gold atom at the corner vertex and these 3 phase centering copper atoms, which again reflects my stoichiometry, which is Cu3Au. So, the motif itself reflects my stoichiometry also. Now, then we considered this example wherein my ordering got a little more complicated. There were non-equivalent positions of the same kind of atom, and also the unit cell became rather large. So, you can see here in this case also the unit cell was about 3.75 angstroms in dimension. This also was tetragonal, but less than 4 angstroms, but and we saw that as we get to this more complicated example, my unit cell gets larger and larger. That means these are more long range ordered structures. And just to summarize the slide, whenever I want to understand these more complicated structures, not only I look at the lattice, the motif, I also try to understand the coordination polyhedron around these individual atoms. I try to identify if my understanding of face centered cubic, for instance, lattice is obeyed. For instance, the coordination polyhedron around all the face centered atoms connected by the face centering translation have identical coordination polyhedra, and also wherever possible I will try to break up this even the coordination polyhedra into sub polyhedra and then assemble my larger polyhedra to understand the crystal structure. So, all these visualizations are very important when I try to understand this more complicated versions of these structures. Yeah.
As you have told that as we are going from easy to simple to complicated structure, the lattice parameter is increasing. Is there any role of lattice distortion also in the increasing lattice parameter?
Okay. Let me try to understand the question. You are asking that we are going from simple to more complicated structures as we are considering more and more sophisticated forms of ordering. What is the role of lattice distortion? There are two kinds of lattice distortions we are talking about: the regular ones which lead to a change in symmetry of the structure, and the irregular ones which are typically found in solid solutions. Because in solid solution, a local region, if I take of space, atoms randomly occupy every lattice point's position. So, whenever I am talking about a lattice parameter, I am talking about an average lattice parameter. So, locally there are a lot of distortions to, suppose I am considering a cubic shaped unit cell, there are a lot of distortions to this unit cell local level, but globally I have a sort of an average lattice parameter. So, that is the sort of a what you may call irregular distortions at the local level, but at the larger level, yes, there are distortions, and we have already seen this example. So, this is an example of a regular distortion. Suppose I had a disordered structure CuAu1, and then what would happen? That it will be a single lattice parameter structure, though it will be a reflection of in some sense of the kind of arrangement of the atoms. But now, since it has got ordered, the symmetry has been lowered, right, and so this has now become a tetragonal structure which is reflected in this T here, right. So, it is a tetragonal structure, and there is now therefore, when this ordering takes place, the Seebeyer ratio will change. So, this is a more regular kind of distortion. So, I would not call this a distortion, but what I might call a dilatation or a contraction in the lattice parameters. So, because the word distortion would mean there is some irregularity to the whole process which is taking place. Yes, therefore, any ordering process will involve distortions, and these distortions could be at the local level or at the global level. So, both these are possible. Now, I have only considered here, for instance, CuAu1, which is a simple tetragonal structure, but there are larger period CuAu2 kind of superlattices, wherein the lattice the periodicity along the fourfold direction increases to large values. So, that is another possibility of ordering in the very same CuAu system. Okay. And we are just considering these in a sequence so that it gives us a simpler understanding. So, we are going from simple to complex not because they are any particular way they are ordered, but simply because to increase our understanding we are going stepwise so that we can slowly try to comprehend more complicated structures, and we have a pathway to understanding certain intermetallics and other kind of structures which have larger and larger unit cells. Okay. So far we have been discussing substitutional solid solutions and their ordering. Similarly, we can also discuss interstitial solid solutions, and when I mean interstitial solid solution, I mean that the alloying element which I am adding, or as I said, there are sometimes equivalent terms like doping or impurity atoms, which now go and sit in the interstices formed by the original parent host lattice or the parent crystal. So, we already and detailed we have already seen the kind of voids which are present in these crystal systems, and therefore, I have options at least in the simple crystal systems like simple cubic, body centered cubic. I know where can these atoms sit. It is however worthwhile to repeat the sentence that there are of course certain very special cases of atoms like boron which can which can sit either in the lattice position or sometime in the interstitials also. But here we will exclusively deal with those kind of elements which sit in the interstitial void positions. And we already seen the kind of voids. For instance, we have seen octahedral and tetrahedral voids in cubic close packed, hexagonal close packed and body centered cubic crystals. And now for an atom to sit in the interstitial position, we have noticed that the atom has to be sufficiently small in size. So here I have a comparison of some of the relative sizes of the various voids and also the relative size of the atoms. So let me look at the smallest atom possible, which is the hydrogen atom, which has a radius of approximately 0.46 angstroms. Now if you go to larger and larger atoms, for instance oxygen has about 0.66 angstrom radius, nitrogen has 0.71 angstrom radius. So this is my nitrogen, this is my oxygen. Carbon has a slightly larger radius of about 0.77 angstroms, and carbon will be an important interstitial alloying element from our point of view, because typically that is a very important alloying element in steel. Boron has a larger radius, and as I pointed out, boron can form interstitial solid solution and in some cases substitutional solid solutions also, and in very other cases can also sit in both positions. Now, so the first rule of something, if it has to form an interstitial solid solution, the atom which for an atom has to be a small in size. So that is one thing we have seen. So let me try to compare these sizes which I have written down here with the relative size of some of the voids which we have already considered. The largest void we saw in the regular structures were the octahedral void in the FCC or the cubic close packed crystal. The next bigger void was the tetrahedral void in the body centered cubic crystal, then was the size of the tetrahedral void in the cubic close packed crystal, and finally the smallest void was the octahedral void in the BCC crystal. And we had also noticed that actually the carbon atom sits in this void in the BCC crystal. So we had noticed that aspect also. So all these voids, atoms which go and sit in the interstitial positions are small, and there is a sort of a general guidance principle or general rule that if the diameter of the atom is less than about 0.6 times the size of the host atom, which the host atom could for instance be an iron atom, a molybdenum atom, chromium atom, or one of those, even an aluminum atom or aluminum ion sitting in the lattice position, then we expect extensive solid solubility. And when I use the word extensive, I do not mean complete solid solubility, but extensive. That means a large amount of solid solubility. Of course, since this is only a rule, and therefore often we will find that in many systems this rule is violated. It is noticed also that the solubility for interstitial atoms is more in transition elements, and these transition elements already you know have incomplete inner shells. Like the transition elements showing good solubility for these interstitial atoms are iron, titanium, vanadium, zirconium, nickel, tungsten, uranium, etc. And some of these, as you know, are very important, commercially important elements. One point to be noted is that carbon is especially insoluble in most non-transition elements. So this is something which is to be noted, and therefore since it is so insoluble, we could actually use a crucible made of graphite to actually melt some of these non-transition elements, because then it will not actually dissolve any carbon. Now, so to summarize this slide, here we are talking about the solubility of an interstitial element, in other words a small sized atom in a parent lattice. Obviously, as you can see that the voids are available are smaller than most of these atoms we are talking about, except perhaps the exception of hydrogen. So for most of these interstitial alloying elements are going to cause distortion to the lattice, and therefore you expect that the solubility is not going to be 100%. That means the number of available voids are going to be much larger than the number of atoms you will be able to put into these parent atoms. As a general guidance principle, you can note that if the size of the atom is less than about 0.6 times the host atom's size, then large amount of solid solubility can be observed. And also it is the electronic structure plays a very important role in the solubility of these elements, and for instance carbon is insoluble in transition practically insoluble in non-transition elements, while many of these interstitial elements dissolve very well in the transition elements. So this is something very important to note. Now before we leave this topic of interstitial solid solutions, it is worthwhile to note that later on we will be talking about interstitial compounds. Okay, wherein the proportion of these interstitial elements will be pretty large, and we should not confuse interstitial solid solutions with interstitial compounds. So, they are different, and in terms of their properties, in terms of their hardness, any one of those aspects, and therefore, they should not be confused with these interstitial solid solutions. Okay. The next big topic we are going to take up now is the compound or intermediate structure. So, let me go back to the slide to revise what are the kind of structures we are talking about, why are we talking about these possibilities. So, let me go back to the original slide where we started off. Here we started off by saying when I add a element to the host lattice, either it segregates, and this is not a very interesting case for study too much, because it means that it is not going to interact with the parent lattice. The second case, which we have been discussing in extensively so far, is the case of the solid solution formation, and we have discussed interstitial solid solutions, which is the last slide, and also substitution solid solution. We also seen very many examples of ordered structures, and in this context of ordering, we have also seen the two important aspects, which is short range ordering versus long range ordering. So, these two important concepts we came across when we dealt with this concept. Now, we are in a position to proceed to deal with the concept of compound or intermediate structures. Now, this is what you might call an ocean by itself, and what we will be taking up here are merely some examples to illustrate some of the important principles involved in the formation of intermediate compounds or structures. And the more important thing we will try to emphasize here is some of the intermediate compounds which form in intermetallic systems are very different in nature from some of the standard valency compounds we have been dealing with in chemistry. Like for instance, normal valency compounds in chemistry have a very fixed composition. For instance, you have to take about water, it is H2O, and there is no chance or no flexibility with respect to the composition, and these compounds, in order to be dissociated, require very high amount of energy. So, we will see that some of the intermetallic compounds we are dealing with do not actually obey many of the valency rules. There is a flexibility in the composition, and therefore, they form a complete class of compounds or intermediate structures all by themselves, which have to be contrasted with respect to the standard valency compounds we deal with in chemistry. In the slide here, it is not an exhaustive collection of all the chemical compounds possible, all the intermetallic chemicals compound, and I am talking intermetallic. I am also including metalloids and other kind of elements, for instance, like nitrogen and carbon, which go into interstitial positions. So, therefore, I am including a slightly larger class than pure metal alloys, but I am talking about metal and non-metal alloys also in this class, but even then this is not an exhaustive list of all the possibilities. The essential crux of the message of this whole slide is that what are the factors which govern the formation of some of these compounds, and as we shall see from these examples, that it could be valency. That means the valence electrons play a very important role in the formation of these compounds. It could be size. So, there are a lot of compounds which wherein size would play a very important role. So, first is valency, it could be size, and many of the examples of why close packed structures form, etc., we have rationalized in terms of the size, that they are all equal size spheres which are packed equally. Then if I are talking about interstitial elements, then obviously again the different kind of aspect of size comes in, which is the radius ratio, not the only the size of the atom, but the size of the atom with respect to the host atom. And in the context of electronic contribution, there is a different one other parameter which is very important, which is the E by A ratio. So, we have very many type of compounds and the galaxy is very large, but we are taking a small sampling here to understand some of the concepts. So, the sampling here includes, for instance, A, valency compounds, B, interstitial phases, which are sometimes called the Hägg phases, C, electron compounds, D, size factor compounds, and the list is very large. Okay. And when I am trying to rationalize the formation of many of these compounds, I identify some of the important contributions to the formation of these compounds, and this could include some very well known principles like the usual principles of valency, or valency coming in or the electron contribution coming in a different form, which is electron per atom ratio. It could be just size factor, or it could be a radius ratio explicitly stated. And even in size factor compounds, obviously there is a radius ratio involved, but in the case of the interstitial phases, the radius ratio is perhaps the most important determining factor in terms of the compound formation. So, we will try to go through some of these cases one by one and try to understand take up some of the examples. Of course, some of the examples are given here, for instance, the Mg2Sn, Mg2Pb, etc., and we will see many more examples here and try to understand how do we rationalize the formation of these compounds. Now, the first thing when you are talking about compounds is that we need to distinguish them from the solid solutions. So, either these could be compounds wherein the atom size is very large and therefore they would themselves form a sublattice, or they could be sublattice, I mean in the sense of in the right of the same size being comparable to the parent atom, or they could be very small and go into the interstitial. So, there are compounds of both types available, and the important thing is that both these type of compounds should be differentiated from the solid solutions, because the properties of the solid solutions are very different from the of the compound. Okay. Typically, they have different crystal lattice. So, they have a different crystal lattice as compared to these components. Many of these crystal structures or many of the chemical compounds have a very complex crystal structures. So, we have seen some examples, but things could get even more complicated. Each component obviously has a specific location or a sublattice of its own. So, this is something which we have already seen. The composition typically can be characterized by a simple formula like A, B, N, where A, M and N are small whole number integers. Now, as we shall see, in this respect these intermediate compounds are somewhat different, that this M and N's have some sort of variability within them in many of the compounds. It is not like every component would have a lot of variability, but there is some possibility of variation. I have already emphasized this aspect that the properties of the product, which is the compound, is very different from that of the component. So, this is something which we have already seen. In the sense of these compounds having a constant melting point and dissociation temperature, they are very similar to the normal compounds. They are also accompanied by substantial thermal effect, which is similar to the normal compounds, and typically they are formed with elements with very different electronic and crystal structures. In other words, what favors the solid solution formation are in some sense some sort of the rules are sort of opposite. We can't take it, of course, these are just not principles, these are some sort of a guidance, understanding, rule kind of thing, wherein you can think of it that if the electronic structure and crystal structure are very similar, you would have a tendency to form solid solutions, and if they are very different, then you would have a chance of forming these kind of chemical compounds, which are, of course, I am talking about still the valency compounds. So, what I mean by these chemical compounds here is the valency compounds. The bonding in the intermetallic compound is usually metallic, but the bonding can change quite a bit on formation of the compound. There is also a possibility that the bonding between a metal and a non-metal could also be metallic. In other words, even though one of the second component in the intermetallic compound is a non-metal, but still the properties of the compound which has formed could be metallic. A large number of intermetallic compounds do not obey valency rules or have constant composition. This is something which distinguishes them from the standard chemical compounds we deal with in chemistry, and this has to be kept in mind whenever we are dealing with intermetallic compounds. So, this is perhaps a very important distinguishing feature which we always have to keep in mind. So, just to summarize this slide, we always have to remember that the properties and the crystal structure of these intermediate compounds are different from the parent elements from which they are formed. Okay. And you could of course have binary, ternary or even quaternary compounds. Though as you go to higher and higher number of elements which form compounds, the number of examples become rarer. That is the number of tabulated examples. The second example I take up here is interstitial phases, or which are sometimes called the Hägg phases. Here again I need to distinguish these interstitial phases or interstitial compounds from the interstitial solid solutions. In interstitial solid solutions, typically the concentration of, say for instance, carbon and iron is usually small. But in the case of interstitial phases, the amount of carbon, for instance, like for instance one example of an interstitial compound could be Fe3C, wherein the amount of carbon is large. Now, transition elements typically form these compounds with elements with small atomic size, and we have seen the example of such kind of elements which have very small atomic size. We have about 4 of them listed here. Okay. The formulae for such compounds typically can be like of the form Mx, where X is the interstitial element. So, it could be mx, m2x, m4x, etc., and some of the examples are given here, and each one of these cases you can see that the smaller sized element is this one and there is a larger sized element which is this one. So, you have tungsten carbide, vanadium carbide, titanium carbide, niobium carbide, and some of these interstitial phases are extremely hard, as we shall see. In the M2X class, we have examples like tungsten W2C, which is a different form of tungsten carbide, MO2C, Fe2N. In M4X class, we have Fe4N and M4N as examples. Clearly, the radiation ratio plays a very important role in the formation of these compounds. So, when I am talking about the radius ratio, I am talking about the radius of the smaller atom Rx. So, this is my x here. So, these are all my x atoms with respect to the radius of the metal atom, which is originally occupying my lattice positions. If the, as I pointed out before, if Rx by Rm is less than 0.59, so this is some sort of a number we remembered before from before, then we typically form, so there are two possibilities, if Rx by Rm is less than 0.59 and Rx by Rm is larger than 0.59. If Rx by Rm is less than 0.59, typically we form simple crystal lattices, like this could be the simple kind of cubic or hexagonal, and the non-metal occupies specific interstitial sites in the cubic or hexagonal crystal. So, this aspect, some of these aspects we have seen before, that why they should occupy specific interstitial positions. On the other hand, if my Rx by Rm is very greater than 0.59, that means that if this if this interstitial atom is going to sit in the parent lattice, then it is going to cause large distortion to these lattices. Then typically you end up forming complex crystal structures, and one of the common complex crystal structure is Fe3C, which is otherwise called cementite, and which is a very important phase which forms in the iron carbon phase diagram. So, even though we are often talking only about the size ratio, we have to note that the valency of the interstitial atom also plays an important role in the formation of these compounds. So, this is an important point to be noted, because these two aspects, the electronic structure and the size aspect, which is of course in some sense coming out from the electronic interactions, are simplified versions of our understanding of the overall reason why certain compounds form or certain existence of certain solid solutions. And one of these could be playing a dominant role, and therefore we often can ignore the role played by the other. But whenever the influence of both of them are considerable, or the effect they play in the contribution towards the formation of a structure, then both of them need to be considered in the analysis. So, even though when I am talking about interstitial phases, the dominant factor seems to be the radius ratio, in other words the radius of the foreign atom which is sitting in the interstices to the radius of the host atom, but the role of the valency or the electronic contribution cannot be ignored. Typically, interstitial phases are variable composition, which is similar to some of the other substitutional or the large atom analogues of this, and the chemical formula indicates the maximum amount of non-metal in the structure. So, this is something which is typically to be noted, even though for instance I may indicate one of these chemical formula structures like MO2C here. This is here my MO2C. Now, the thing to be noted is that this amount of carbon in this formula for instance is the largest maximum amount of carbon which can be present, and you could have a lower amount of carbon in the structure. So, this aspect is again very characteristic of some of the intermetallic compounds or metal metalloid compounds, and which is very different from some of the normal valency compounds we deal with in chemistry. The properties, as I mentioned, changes drastically with the formation of these compounds, and some of these important properties of some of these compounds which are listed is that they have a high electrical conductivity, and this electrical conductivity is similar to that of a metal. That means that the negative coefficient, that means the conductivity decreases with increasing temperature as thermal scattering increases, and it has got metallic luster like you would expect for a normal metal. Many of these interstitial phases are very, very hard. Some of the, for instance, tungsten carbide has found very important industrial applications in cutting tools. Vanadium carbide is another example of a very hard phase, and this vanadium carbide is an important structure from other points of view, which we shall see later. For instance, this comes in the context of what is known as vacancy ordered phases. These carbides have a very high melting point, which goes of course very well with the hardness we are talking about, and there is some covalent character to the bonding in some of these phases. So, even though we are talking about a metallic luster and electrical conductivity, which is characteristic of a metal, then there could be in some cases a certain covalent character to the bonding, and this covalent character would influence many of the properties. So, let me summarize this slide of interstitial phases. These interstitial phases, as I said, have to be very clearly contrasted with the interstitial solid solutions. As you can see from these very many examples, that these interstitial phases have a large proportion of the interstitial element. For instance, in titanium nitride, we have about 50% possibility of having nitrogen. Now, again, going along with this composition aspect, we have to note that the chemical formula is indicative of the maximum amount of the non-metal, and not necessarily that all the amount of non-metal which is indicated with the formula need to be fulfilled. The common examples of these kind of for instance interstitial phases are, they have these mx kind of formula, m2x kind of formula, and many times m4x kind of formula, and there is also this possibility we have seen here Fe3C, which is for instance m3x kind of formula. Okay. The important thing, as I mentioned, is the size factor ratio, and two possibilities exist. You get very simple crystal structures like cubic and hexagonal when the radius ratio is less than 0.5 or less than 0.6, and when the radius ratio gets larger than 0.6, then you can get very complex crystal structures. As I said, even though we are only considering mainly the size factor, valency also plays an important role in the formation and in the properties of these compounds. The next possibility, let me go back to the table where we are considering this. So, we already considered this valency compounds here. So, this part we have considered. Now, we also considered interstitial phases. Now, let us take up these electron compounds. Now, in electron compounds, as the name suggests, it is not the size factor which is the dominant factor in the formation of these compounds, and it requires a special attention for us to understand why these compounds form and what are the E/E ratios at which they form. These compounds typically form in monometal metals, transition metals like iron, cobalt and manganese, and some other metals also with other kind of valencies. So, you can see some prominent examples here. For instance, in this table here, like for instance copper zinc is a very prominent example which forms more than one kind of an electron compound. Now, the more frequent ones which form electron compounds are as alloying elements are the elements which are present are copper, silver and gold. Okay. Now, the important characteristic of these electron compounds is the E/A ratio in these compounds. That means, all the compounds which form are stabilized by a certain E/A ratio. Of course, the chemical formula itself will only tell you the number of atoms, and the electrons have to be counted from the valency of these atoms. Okay. So, what I find out that if there are certain elements, certain compounds which are being stabilized here, like these very simple ratio ones like Cu3Al, NiAl, Cu5Cd or CO5Zn21, which is of course little more complicated in chemical formula than some of the simpler ones. Now, all these compounds are being stabilized for a specific value of electron to atom ratio. Okay. Now, what are these electron to atom ratios? These electron to atom ratio, there are three possibilities. One is 21/14, the other one is 21/13, other one is 21/12. Of course, I could reduce these numbers to smaller fractions, like 21/14 is 3/2, which is 1.5, 21/13 is of course can't be reduced further, but it is approximately equal to 1.62, and 21/12 is 1.75, or which is 7/4. So, it so happens that in these electron compounds, when the E/A ratio is the specific ratio, then you find that certain compounds are stabilized. Now, why do I divide this into three different types based on these E/A ratios? Is that when I have a 21/14 ratio, which is 3/2 ratio, then you typically find that the crystal structure which forms is BCC, complex cubic or hexagonal, and typically these compounds are called beta compounds. Now, how do I calculate the E/A ratio in these cases? Now, let me take the example of copper zinc. Now zinc gives as a valency of 2, copper as a valency of 1. Therefore, there are the total number of electrons in the system is, so now I am considering the example of copper zinc. So zinc has a valency of 2, so this is my valency, and copper has a valency of 1. So total number of electrons
is 3.
As you can see from the chemical formula, atoms, total number of atoms is 1 plus 1, 2. Therefore, my E by A ratio is the number of electrons divided by the number of atoms, which is 3 by 2, which is what is the number which is stabilizing my 21 by 14 or 3 by 2, and these kind of structures are typically BCC, complex cubic or hexagonal, and all these are called beta compounds. Now when I have a 21 by 13 ratio, which is 1.62, then the crystal structure is typically more complex, and these compounds are called gamma compounds. So these are my gamma compounds. And similarly, whenever I have a ratio of 7 by 4 or 1.75, then these structures which form are called epsilon phases, and the crystal structure is hexagonal, and there are these examples to these. Now let me try to make a calculation for instance this Cu5 is at an 8. So I have the next formula, which is, I have Cu5 is at an 8, and so number of atoms is 8 plus 5, which is 13 for this compound. The number of electrons, because this is valency 2, there is 16 plus 5, 21 electrons in this compound. So I have my ratio as 21 by 13. So this is my second case. So after this first case, I have my second case, wherein I have 21 by 13 electron by atom ratio, and that stabilizes. That means Cu5Zn typically has a very complex crystal structure. Now of course I could make a calculation for some of these other cases. For instance, in this case Cu3Al, aluminum would give 3 electrons, copper would give 3, there are 6 electrons, and there are 4 atoms, which again gives me my 6 by 4, which is 3 by 2. Okay. So suppose I am talking about Cu3. So the number of atoms in this unit cell is 4. The number of electrons is 3 2s are 6 plus 1 7. So I have my E by ratio as 7 by 4. And since this E by ratio is 7 by 4, I know that this will be having a crystal structure which is hexagonal, which comes from this specific E by ratio. Again, as before, many of these compounds can form over larger composition ranges. That means that these are, even though these are called compounds, they are not line compounds, and there is a variability in the composition. These compounds, some of them can actually get disordered on heating, which means that they are actually showing an order disorder transformation as well. So just to summarize this slide, which is highlighting a very important class of compounds, which are the electron compounds, and in some contexts wherever E by ratio is the mechanism responsible for stabilization of the crystal structure, then I sometimes these are referred to also as Hume-Rothery compounds also. Now there are 3 important classes of these electron compounds: those which are stabilized with E by ratios 21 by 14, those which are stabilized by E by ratio 21 by 13 and 21 by 12, and the crystal structures correspondingly for these 3 types are BCC, complex cubic or hexagonal. In the typical 21 by 13 you have a very complex crystal structure, and in hexagonal crystals are the ones which form with 21 by 12. And as before, as we noted for some of the other compounds before, the composition can be variable, and these can also show order disorder transformations. Now in this class of let me go back to the slide where we are describing these class. In this class of chemical compounds we are talking about, we now take up the 4th class, which is the size factor compounds. And there are of course many possibilities here. We take up 2 important classes, which are the Laves phases and the Frank-Caspar phases. These Laves phases, and as we shall see, they are a very important class of compounds, and there are more than 1400 members which are known in this class. So it is a large class of compounds which come under the Laves class, and they are all size factor compounds having a formula of AB2. So here we are describing actually a very large class of compounds, and these compounds are called tetrahedrally close packed compound structures, and we will take up some example to understand these tetrahedrally close packed structures. And for an ideal C-by ratio, they have an ideal C-by ratio of the atoms. Suppose I am talking about an AB2 kind of compound, then you have an Ra by Rb which is root of 3 by 2, which is approximately 1.225. Even when the Ra by Rb ratio is sometimes not around, is exactly not this ideal value or around this ideal value, then you would still form a tetrahedrally close packed structure which has this kind of a formula, which is AB2. Now, the important crystal structures which form under this Laves class are typically designated according to the Structure-Beerisch notation as the C15, or let me start with C14, C15 and C36. So, there are three important classes of Laves phases: the C14 class according to Structure-Beerisch notation, the C15 class according to the Structure-Beerisch notation, and the C36 class. And there are typical members which are called the what you might call the representative members, and they are, for the C14 class it is the MgCu2 structure, which is called an FCC lattice. For the C15 class it is MgZn2, which is hexagonal, and there is a more complicated in having more number of atoms, which is MgNi2, which is also from the hexagonal class. So, the important thing to be noted is that there are many ternary and multinary representative Laves phases with excess of A and B elements also. Some ternary Laves phases are known in system with no corresponding binary Laves phases. Okay. So, when I am talking about ternary Laves phase, I mean that some of these elements A and B are being replaced in the structure with some third element C. Another important thing, again as we have seen before, even though we start off by saying that the important influencing factor is usually either an electron to atom ratio or a size ratio or a size factor, then obviously we cannot ignore the other aspect, which is the electronic structure of the material. So, it is also seen in many cases, especially in these ternary Laves phases, that the E by ratio plays an important role in the formation of these compounds and stabilization of these compounds. So, let me summarize this slide before we take up the examples, which of course we will see a few. That these Laves phases represent a large class of structures, and typically they have a formula AB2, though we could have ternary variants of these also. And when I am talking about ternary variants of these, we should understand that in many of these cases the electron by atom ratio is also playing an important role in the stabilization of those ternary variants. The ideal Ra by Rb ratio around which these compounds form is about 1.225, and these are called the tetrahedrally close packed structures, okay, which is in some sense a variant of the close packed structures we have been considering, wherein we have had only one element which was there. And even in the single element case, we have already seen that if you talk about the local polyhedra which forms between two layers, it is the tetrahedron. And the three important representative members of this class, two of them belonging to the hexagonal class and one belonging to the cubic class, are MgCu2, MgZn2 and MgNi2. So, the common factor between all these representatives being Mg. The Laves phases containing transition elements as components have interesting physical and mechanical properties, and slowly there are a lot of engineering applications for these Laves phases are being developed, and some of these applications are for high temperature applications, like for instance in turbine blade, fine precipitates of Laves phases have been shown to improve fatigue strength. In hydrogen storage applications also, like in nickel metal hydride batteries, Laves phases are slowly finding applications. The diagram below shows the electron to atom ratio effect in the formation of some of these three typical structures. So, we already seen the three important structures, the MgCu2, the MgNi2 and the MgZn2 structures, and it is seen here depending on the E by ratio in some of the systems. For instance, let me take a example, the magnesium copper aluminum system, or let me take the simpler example, the magnesium copper zinc system. In the magnesium copper zinc system, for an E by value up to about 1.8, it is seen that you form an MgCu2 structure, and between value 1.8 and 1.9 approximately you form the MgNi2 structure, and a value around centered around 2, you form the Mg(Zn2) structure. In other words, in these ternary Laves phases, the electron to atom ratio has an important role to play in the formation and stabilization of these structures. So let me take up examples of the C15 structure and the C14 structure to understand the Laves phases and how these structures look. And as we are considering these structures, we will also, as I said, our goal is twofold here, not only to understand what the criteria these compounds form but also to slowly introduce ourselves to more complex structures and more examples of these what you might call hexagonal and cubic and other kind of phases which form. So this is here the Mg(Zn2) Laves phase, which is as a structure we read notation, which is C15, as a structure like this. In the Pearson symbol, it has got a symbol Hp12. That means it is hexagonal, it is primitive. As we know, there is only one lattice in hexagonal, which is primitive, and there are 12 atoms in the unit cell. So even though it is hexagonal now and it has got the same symmetry as that of the normal hexagonal close packed crystal, which is P63 by mmc, it is still a unit cell with a larger lattice parameter and it is having more number of atoms. It has got 12 atoms, unlike the normal hexagonal close packed crystal, which is only 2 atoms in the unit cell. So this is a higher order or a more complicated version of an hexagonal crystal as compared to the hexagonal close packed crystal. Now the magnesium atom is the one which is in blue, and the zinc atoms are in the violet color, the dark violet and the light violet color, or both here are in the dark violet color. So you can see that this is the unit cell, and if you look at the 0001 projection, this is my 0001 projection of the unit cell. So you can see in the projection that these blue atoms are located at the centroids of the, so if you draw a triangle, the half triangle, so these magnesium atoms are located as centroid at various positions, of course not at the base but some other various positions. And if you look at the zinc atom, of course one is located at the 000 position, but you can also see that they are located at C position from the 0.062 magnesium atom. Now so this is slightly above the basal plane. Now the best way to understand these structures is looking at why I call them the tetrahedrally close packed structure and how I can understand them by some of the usual rules of packing which we have seen before. Even though these unit cells are pretty instructive, you can see that even from these unit cell that there is this triangle of atoms within which I can visualize this now my blue magnesium atom here. But the more instructive way to look at these is by looking at these kind of diagrams. But before I go to that, again you should notice that if you look at the Wyckoff symbols, there are two kind of zinc atoms here, right at the bottom here. There is zinc 1 and there is zinc 2. So the zinc 1 is the one which is located at the vertices here, and the zinc 2 is the one which is located at C equal to 0.25. That means it is 1/4 the distance in C direction. So this plane is 1/4 way up. So how do I understand the formation of these tetrahedrally close packed structures? I can start with a hexagonal array of zinc atoms, and as you can see in this hexagonal array I have not taken my central zinc atom, right, that is not there, but I can get an hexagonal net of atoms as shown here. So this is somewhat related to the Kagome net, which many people must have heard. So you can see that there is an hexagon here and there is a triangle here, right. So this is my hexagonal array with these triangular networks in between. Now what I do, I starting with this kind of a net of zinc atoms, I put my magnesium atoms. And where do I put my magnesium atoms? The obvious choice is these places. Zinc being the smaller atom, I form the net first of the zinc atoms, and magnesium is the larger atom, which I place in this depression formed by these array of zinc atoms. Of course I have two positions in which I put these magnesium atoms, and I put them on both those positions, that is one above this layer and one below the layer. So if you go to the diagram above, you can see that if you have a positions of the zinc atom, for instance here, then I can put magnesium atoms one above and I can put one below also, and which is what I do. I put them in the depressions. Now what I do further is that to make the next layer, That means I have constructed 3 layers, one layer of zinc atoms as in the net here on the left hand side of the picture. Then I put one magnesium above the net, of course only one of those positions I have seen for instance, and one array of magnesium atoms below the layer. So I got totally 3 layers, but one of those magnesium position layers only is shown here. Then to construct the next layer, I can put my second layer of zinc atoms. So there is already one layer of zinc atoms, the second layer of zinc atoms at the depression formed by these 2 layers. In other words, suppose I am looking at the layer from the top, that means I am inverting, let me switch to the highlighter. So looking at this diagram, suppose I am having these magnesium atoms here and I invert my layer, that means I look from the other side, then I can see these magnesium atoms sitting like this here. And what I do is that now I have a depression formed by these magnesium atoms and the previous layer of zinc atoms, and I put zinc atoms in these new positions. So these are, for instance, let me choose a different color for showing you these atoms. So I can see that these are my layer of zinc atoms. So on completing this procedure by putting, of course, starting with one layer of zinc atoms, then I put 2 layers of magnesium atoms, then I can put of course, as I did here, another layer of zinc atoms, and of course correspondingly on the other side also of the layers I can put other layer of zinc atoms. I would get half the unit cell along the C direction. So the half the unit cell consists of this zinc layer, the magnesium layer, and the other zinc layer, and of course I can proceed in both directions to complete the structure. So as you can see, I am following some of the principles which I used when I formed a single element close pack construction. That means I started the array of atoms, a layer of atoms, I locate my depressions in that layer and start putting the next layer, and this is what I am doing here. Only thing, the starting configuration is somewhat different from the starting configuration which you normally see in many of the other, in the normal close pack crystals. So these are called the tetrahedrally close pack crystals, and some of the principles are as before, and we can understand these structures by starting with layers of atoms. Now the next structure we consider is the C14 Laves phase, which is typified by the formula MgCu2, and this is again a very frequent structural type. Laves phase themselves are splendorous in number, and this is another frequent crystal structure type. This structure, unlike the Mg2, which has got hexagonal symmetry here, you can see this is an hexagonal kind of symmetry, these crystals have cubic symmetry. And let us try to understand this crystal structure, which is not very difficult to understand. So they have the space group Fd 3 bar m, and this D here tells me that this is a diamond cubic structure. The Pearson symbol tells me it is cubic, face centered, and there are 24 atoms in the unit cell. Of course, I can make a counting of these 24 atoms, and one way to do it is looking at the Wyckoff position. There are 16 of those are copper and 8 of them are magnesium. So the 8 magnesium atoms, of course, I can count very easily, because there are all in the face centering position to contribute 4. In addition, there are these 4 which are located within the unit cell, which give me which are a tetrahedron themselves, because that is why they are, as you know, in diamond cubic structures you have this kind of a symmetry, and therefore there are 4 of them, making a total of 8 atoms of magnesium within the unit cell. There are 16 copper atoms, which also I can go about counting, and I will get 16 copper atoms in the unit cell. Now how do I understand this structure? So let me get to some of my, as I said, these are all tetrahedrally close packed structures. So what I do, as before, I start with the net of these atoms. In this case, of course, this is my the blue is my magnesium atom, and the other violet color is my copper atom. So I start with the copper atoms, which are located in the form of this original net. Of course, I have shown only a part of the net in this diagram, and now I am looking along the 1 1 1 direction of the cube. So I have to note that this is my one direction of the cubic crystal structure, and this is not obviously a simple cubic structure, but this is a face centered cubic, and the precise kind of structure, it is a diamond cubic structure. So now I have this layer, and within this interstitials, as before, I put my magnesium atoms. So this is, let me go back here. So these are my magnesium atoms, and I put my magnesium atoms in the voids formed or the depressions formed by this layer of copper atoms, and then additionally I put another copper atom here in the void formed by these magnesium atoms and the void of the previous copper atoms. So, I get a second layer which is like this. Then I can make higher layers by putting this light blue and dark blue both refer to the magnesium atoms which are in the unit cell here, which is the larger atom. So, the magnesium atom is the larger atom, the smaller atom is the violet copper atom. So, I put more of these magnesium atoms again. So, I have a, for instance, a magnesium atom here and I have a depression here. So, I can put it in this depression. So, I form the third layer, okay. And this third layer now consists, if you look at this layer consisting these blue, then you would note that they themselves are a hexagonal array, but of course not touching each other. Then further I can make another layer above that by putting these copper atoms, which are the smaller atoms, 3 of them, in the gap formed between these 3. So, I take this gap formed by these 3 and I put 3 copper atoms there, and so forth. I can proceed in that gap formed between these 3 copper atoms. I can put a magnesium atom. So, all these blues, the dark blue, the somewhat fluorescent blue and the very light blue, all of them are magnesium atoms which are the larger atoms. The copper atoms again are shown in light violet or dark violet. There are 2 colors we have used, and we can put more of these, and finally I can put a magnesium layer. So, I can go on making these kind of close packed structures which are tetrahedrally close packed. As you can see now, you can identify these tetrahedra very easily. For instance, these 4 atoms, let me mark them with crosses, and this one at the top, these 4 form a tetrahedron, right. Clearly they form a tetrahedron. So, at each layer you can identify these tetrahedra and how these structures propagate into filling complete space. And the important thing, of course, we note here is that even though we are starting with layers which are hexagonal, we are ending up with cubic symmetry in this case. So, if we look at projection, so if I note that in my color coding, it means I have an understanding of the color coding, that the lowermost layers are the violet colors, the next higher layers are light violet, etc. Then I can note them in projection like this. So, just to summarize these 2 Laves phases we have seen so far, there are 3 important classes of Laves phases: the MgZn2, the MgNi2 and MgCu2. We have taken 2 examples to understand the structures, that how they are tetrahedrally close packed, the MgZn2 which is hexagonal and the MgCu2 which is cubic. And we have tried to understand these structures by starting with layers and putting more and more atoms in above and below layers to form the entire structure. So, these are 2 important Laves structures, and the next topic we take up are Frank-Caspar phases.